Hello everybody. The topic of today's webinar is to explain you one of the neural network techniques called UVQ, and supervised neural network, and how it's used in our seismic interpretation software, OpendTect. Yeah, I said one of the neural network technique as the other one type of neural network, it is supervised, was fully explained in one of the webinar earlier, some months ago, by my colleague David Connolly. So to start, I will first explain some key points in the PowerPoint before using the OpendTect software for the demo. The main point of the presentation are UVQ introduction. Here I will talk briefly about the definition of UVQ, the objective, the workflow, and the concept behind the UVQ, how the algorithm works behind the scene. Then I will show you different types of UVQ, horizon-based and volume-based. Finally, at the end, I will live demo the UVQ clustering in OpendTect. The introduction. UVQ stands for unsupervised vector quantizer. This unsupervised neural network technique is used here to cluster your seismic data. It's like, let's say, a natural way of segmenting the data. And it can be done along the horizon, 2D horizon, 3D horizon, and also in the volume or even between horizon. It's also useful to highlight and analyze a seismic pattern that can be subsequently be interpreted. Let's say, example, some geomorphological patterns, some channels, some DHL anomalies. The UVQ workflow. We see here in this slide a UVQ workflow which will guide the user from the input seismic data and mapped horizon to the output segmentation and match grid, you can see here. This is a workflow that we call conventional or standard. The user has a full control in selecting the data point or pick set. Like you can see here, it's create pick set. You can choose how many picks you want, and you define your attribute. So the difference with the second one is workflow, which is called quick UVQ. This specific workflow, this specific technique, like it's called quick, is really quick. And however, this is done only on the horizon. This cannot be done in the volume. And in this quick UVQ, all the input set, like training, finding the pick set, and setting up the attribute are set automatically. But in the quick UVQ, the user still has, let's say, the control on the parameter, like the class center, defining the class and setting up the time gate. So the UVQ concept, how it really works. So I will try to explain it here. The data is clustered in, let's say, the hyperspace dimension, which is dimension 4 and higher. But to easily explain it here, you see that I just use two-dimensional, let's say x1 and x2. So x1 and x2 are used as being input attribute. So random locations are taken from the input seismic data. So data points are extracted. So it's extract the attribute at those random location. These data points are mapped back in the hyperspace, which is two-dimensional here. So let's say you have, for instance, one attribute here and another attribute. So it's mapped back here in this two-dimensional space, and we define the number of cluster center. Here shown as the star. So in this case of two-dimensional, we have 3 class center. It's a user-defined, so 1, 2, and 3 here. So during the training, actually the objective will be to have those class center placed here in the center. So this one should be going here in the clustering, and this one coming down here in the center of the data point, and this one also coming down here. But this task actually, like you can see here in the two-dimensional, it's much easier, but we are actually talking hyperspace. So instead of having x1 and x2, we can have like 5, 6 input attributes. So it's much complicated to find those center. So how it works actually? So the principle is as follows. The algorithm is run one by one in all data point. Such data point is selected here. The all cluster center are examined. So examined. Here the case is 1, 2, 3. The Euclidean distance is calculated, and the closest one move toward the selected data point. Sorry. So this type of iteration is done also here. So it will find the closest by calculating the Euclidean distance, and this one is much closer, and it's moved a little bit. Same thing from here. So we do that for the all data point. The data point are visited multi-time, and at the end we will have something like that. So at the end we will have that at each the cluster are finally placed in the center. So when the training has finished, the second phase will be the application. So the application phase, the output is actually 2. The first one, a number is assigned to all data point based on the distance between the data point and the closest class. I will explain. I have, for instance, a data here. So based on the distance, so this is class 1, class 2, class 2, 3, for instance, this one will assign a number 1 because it's closest. And this is the first grid, so the first output grid, this is the class grid, and the second one is a match. The match is just the distance, how close and how far this data point here is to its class center. The closer the distance is, the higher the match. The further it's, if it's like let's say somewhere here, it will still be assigned in here, like say in class 3, but the match will be, let's say, 0.85 or something like that, but less. So this is actually how the algorithm work. And let me go ahead to talk about the type of UVQ, horizon-based, which is waveform driven, but you can still use other type of attributes to use as input. So here we'll talk about the quick UVQ horizon option. It can be used quickly to segment seismic waveform along interpreted horizon, and it works in for 2D and as well for 3D horizon. The user input only time gate. It can be waveform and the number of cluster, like I explained in the workflow. So the time gate is driven by geology, for instance. So let's say a thickness of the target formation that you want to evaluate. So you look first at the geology and decide what type of time gate. And the number of class center, it's depend actually. So the default in OpendTect is 10, but you can increase or you can decrease depending on the type of the data. But we will go through those through the demo, and we'll look how we can do that. So the training and application are done automatically for the quick UVQ, but always don't forget to save your output grid. So here is an example of UVQ horizon-based, a 3D example. So like you can see here, the input is the waveform and the output is thickness and anomaly. So here I will explain why output is thickness and anomaly. Like you can see here, the reference horizon is here, is mapped on a good peak. It's also one of the first condition that your horizon should vary when we should be well mapped in order to have good result. So the first output, I say it's a thickness, because if you look at those class starting from 1 till 6, we don't look at the horizon here, but you will see that there are a quite trend here going from class 1 and class 5, and that's why we might think that it's a thickness trend. But we say might because it's not for certain, because it can also be something else like acquisition type of trend. And the second one is the class 6 and 7. It's said anomaly because just by looking here, we have those similar peak, similar trough peak, and here we have something going on here. Small, low amplitude, but high amplitude. So maybe something related with hydrocarbon type of anomalies. But once again, the result should be integrated with other type of input in order to be sure about the interpretation. A quick, an example of 2D UVQ coarse grid on coarse grid 2D horizon. How we can improve the result. You remember earlier I said that the number of class depend, is very difficult to find. Here we start with, let's say, 10 classes and with high time gate, -4t plus 72 milliseconds. But the first UVQ had rather large time gate, and several classes are similar. Therefore, it is decided to reduce the number of classes. So we reduce the number of classes to, let's say, 5, and it's still, because of the time gate, the results are not quite okay. And the final one is here, best UVQ that we find for that data set. But, like I said, but the result can be not reliable because of the horizon, which is not very well mapped. So like you can see here, it's going on peak and then on trough and peak again. So the idea will be to go back to your mapping, or if you want, you track again your horizon, or you snap it to the nearest event, which is the peak in that situation. And the dense grid, the first example, it was just a course, so we had some problem here, for instance. But with the dense grid being dense, so you have the possibility the possibility to map very well your horizon on which you want the clustering to be done. So like here you can see the grid was really dense, and we mapped a top of horizon, and UVQ was done on that top of the horizon. We look at below, and we came out with that clustering. But I will show you that in a demo. This is actually in blue. You can see it's this class, for instance, with high amplitude, and knowing the data, it can be seen here like carbonate limestone carbonate banks from the Abenaki formation in the Scotian shelf. Like you can just see here, so we are somewhere here, so this blue. So based on the morphology, again, we can see that, okay, it's something similar, that those blue classes actually show us that they are can be seen as carbonate bands. So multi-attribute training along the horizon. So I said earlier that waveform segmentation can be used for horizon-based, but other type of attribute also can be used. I will show you an example here. So when the waveform segmentation alone does not give satisfactory result, the multi-attribute can be used as input for the horizon-based segmentation to better highlight the geological and structural feature. In this example, we cluster the data by looking below here, and then this is the result. When zooming, we see that the faces are really scattered, and like you can see here, it's very difficult to predict any geological feature with certainty. So what we do further is that we add more attribute. The waveform alone do not provide any geological trend, like we just explained. So the step further is just to extend the training by adding more seismic attribute to use as input for the clustering. So here we use, for instance, acoustic impedance. We use a different type of spectral decomposition, 12, 15, 25, 30, 35 hertz. And we also use the same UVQ segment that we got from the first result. So the result is already different. We can see some trend here. You can see here. Going into deep, we could divide it into different class. So you can see anhydrite, like shelly facies here, dolomitic facies, and yeah, dolomitic plus shelly. So actually, that is the way of doing. So if you're the first time that the result of waveform alone does not give you any good result, just go ahead and continue by adding more attribute. The volume-based segmentation. So instead, for instance, of clustering attribute using horizon, it's also possible to cluster attribute in the volume. So the 3D segmentation scheme is similar, but only attribute not directly related to the phase should be used. So I will explain. When using waveform, we know that it's phase related. It's done for a 2D, for instance, type of clustering, 2D, 3D horizon, horizon-based clustering. But if you use, for instance, volume-based, please try to use attributes which are phase independent. If you will use still, let's say, attribute like amplitude, the result will be similar as the original seismic data. So example of seismic attribute that can be used, like energy, for instance, spectral decomposition, frequency, horizon cube attribute, and also a new implemented attribute called texture in new implemented in OpendTect that I will also talk a little bit about it. So horizon cube attribute, like you can see here, we have density attribute and we have thickness attribute. Both shows area of pinch out in conformities and condensate interval. The texture attribute, newly implemented in OpendTect, so it's a group of attributes that return a statistical property of gray level concurrence. GLCM texture attribute come from image processing and were developed to capture like roughness and smoothness of an image. So actually how to work, the attribute response is calculated in 2 steps. First, the GLCM is computed from an area, let's say a volume, around the evaluation point. And secondly, a property, a statistical property from this GLCM is returned. So this is quite an example of different type of output that the texture can output. So using this texture attribute, those kind of output that we can get. And if you still use deep steroid attribute, you can use the option of adding a steering cube, and the result will be still much better. So this is an example of UVQ volume-based clustering. Many attribute phase independent was used. Like you can see here, we can look at this huge meandering channel here that can be seen and can be isolated using volume rounding for further interpretation. So that ends the first part of the webinar. Let me just go quickly to sorry. So I directly open OpendTect. The version is 4.4 D. What I will do here, I will just first display an inline. So the data is F3 demo, a Dutch block in the North Sea. Like you can see here, inline 425. I will display the horizon. I want the UVQ, 3D UVQ to be done. Is maximum flooding surface MFS4. If I will display it at section, so you remember we want to find the time gate. So what we are looking here is a maximum flooding surface, which can be seen as an unconformity, because below you have a type of translation package system track, and above it's starting the regression. So like you can see here, some of those prograding trend downlapping on the surfaces. So being an unconformity, so that means that what we will want to do, we will try to avoid, if we want to look at below, we try to avoid taking a sample above in order to avoid the interference. So for instance, here we can see those like channel cut here in the section that we would like, for instance, to look at how it will look in the map view. So let's say if we will go to our horizon and right-click workflow, quick UVQ, what will happen here? The window open up, and it's telling us that the input data should be selected, but because it's already set as default, so we have a deep state medium filter, which is a filtered type of zero seismic. Noise has been removed, and seismic event has been enhanced. Here the number class is set as 10 that you can reduce or you can add. Let's add, for instance, more. Go to 16 classes. Time gate. Let's avoid the interference above. I can use 0, or even I can still even avoid more by using one sample below the horizon and 24. I can use a polygon, but I will not do that. I will just use the data will be calculated on the whole horizon. And here I can save it, for instance, UVQ test, for instance, but always try to give a very good name so you can remember when you will open it. So when I will click OK, so you can see the training start already quite well, going up to 90%, which is good. And if it's not good, for instance, you can pause or clear and it will start again, or you can look at the data and go back. So those are the vector trend. Because it's a UVQ, quick UVQ, so we don't know actually how much the peak set has been used, but it's normally between 2,000 and 3,000, something like that. So we can click OK directly, and it's going to apply the network, and we will have two output. So this is the neural network info. So you can just take a look at those statistics, for instance, or those are the class, those are the number of vector. Always take a look at it, and if sometimes you can see that there are less vector for class, maybe something like 20 or 30, and here also average match, if it's below, let's say 85%, you can go, you can dismiss and go back, try to remove class and retrain again. This is the advantage of clustering of neural network, which is, let's say, an iteration process. You can go back and look. For the input node relative importance, which is not really good in that situation, is only when you use different kind of attribute. Here we use only waveform. So you can also look at the difference in the center here, but also good for multi-attribute. And I can click on, I can save my report for further use for later retrieval. But if I click on display here, what I see my classes. So from 1 up to 16. You see how they are different in shape, different in amplitude and frequency. Some of them are close, showing some trend, thickness trends. So some are just alone, like this one, low amplitude, low frequency. And what you can do also, you can use the color bar. Let's say 16, for instance, here, which will show you the class by color. Let me minimize it and dismiss, and I will display my my horizon in full in order to see the result. This is how it looks like. The color bar, which has we're looking here, it's the Sesame color bar. So we have the match here, and we have the class. So by looking at the data, please always play with the color bar, because the color bar will show you, different color bar will show you different type of, give you different type of information. So what I will do here, I click here, and I will just try to scroll in order to find the color bar which will best match my display. So I can play around and then display the one which will give me a good display. So let's click, for instance, this contour gradient, because the contour gradient actually use a contrast, so it show you different kind of so the color are really separated. And here already we can see some feature, some nice feature here. You can see it's in the this is like a channel, look like channel going down to the basin, where it's becoming like a fan system here. Here we have some sand ridge. Here we have some quite difficult area to try to interpret here. So this is actually what we have. It gives you an idea of the data, but you can go beyond it by doing like stochastic modeling, which will give you more information, what you want to try to confirm. If you say, okay, this is a channel, by adding more input data, you can confirm it or not confirm. So this is actually how it does. So this is the first way. And the second one, I will not demo it, but I will just show you the result. So what I did is I use the polygon here. Let me just display it. I'm sorry, I just show you the class. I did not show you the match. So this is actually the match, how it look like. So the match, like I explained earlier, it show you how close and how far the data point are to its closest class center. But the thing you will notice here is that it can also give us good information. look at this channel, for instance, they have been highlighted. What it does explain is that they have low classes. The array of low classes. It's also give us, like an interesting feature, like channel in those, like I just said, the deep water. This is, we can explain it with the algorithm, why we came out like that. Is that this channel contains very small limited area, so it's not very well sampled. So you have it here, you don't have it somewhere here. So the neural network cannot find those class center, so they could have their own class. Because they don't have their own class, they have been attached to other classes, but the match is low, like we can see. But it gives us some result. So I was explaining also that by looking at the result, you can go beyond that. You can extract your data using the polygon, for instance. So this is what I did. So I just use some polygon here, and the result, let me just show how it's really look like. So this is how it look like. I'm not going to do that, but when you will click, for instance, workflow, quick UVQ, here you have polygon selection. So you can go and select, so just to constrain your cluster to a specific area. So this is how it look like. It shows more information compare, for instance, by using the clustering in the whole data. Let me quickly go to a second. So this is the 2D horizon clustering. The data is Penobscot 2D. In a Scotian shelf, a Scotian basin. The data is available in our OpendTect seismic repository. For those who want to work with the data, you can download it from opentect.org/OSR. So let me just go quickly show you the top of horizon. So this is the top of the horizon, top of Abenaki formation. So we do the same thing, quick UVQ. And here, I also just want to restrain my data here in the polygon, like you can see here. So let me just remove the polygon. You have some visualization problem. So right click, quick UVQ, attribute is there, and the number of UVQ classes is 10, for instance, time gate -8 plus 24. We want to look below, but we want to take some more sample above. This one, contrary to the F3 where it was an unconformity, but here we have like carbonate below and some shelly sediment, shelly type of deposition above. So we just want also to see a little bit of two sample above it. So pick top. I select the polygon selection here. I can save it or I can just move. So by clicking OK, it will train. But here also I just don't want to go beyond. But the good thing here with the 2D data, let me just go, no problem. I think maybe I still have some time. So it's extracting the data, but using the 2D data, what the algorithm does, it's after extracting, after clustering, and when it wants it to apply the result, to segment and match, the window will pop up asking the user to select the 3D horizon. If there is no available 3D horizon, the same window allows the user to create a 3D horizon by using different type of grading algorithm. We have triangulation, extension, and inverse algorithm, you name it. So this is the training. It's also start well, 90%, 93%, which is good. I just click OK, it will apply, and then I will not wait for the result, but just want to show you the window. So specify the destination for output. Destination 3D, or you can output it as an ASCII file. So here 3D, those are the different type of algorithm you can use: inverse, triangulation, extension, continuous curvature, and nearest. And the search of radius. So what I do here, I already have an horizon that I will add, and you can specify your class. You have the option of adding the match, but I will not go through. I will just dismiss it to show you the result, how it looks like. So here, Abenaki classes. So this is the extension 100. So we have, those are 2D lines. So the extension, you can use different type of steps. 20, those steps are actually the bin. So it will do, just depending on the grading algorithm, it will just do some interpolation. So this is one of them, and this here I use the extension 20 only. So you can see here how it's so those are the densely spaced 2D line, and you can see that you have your UVQ here. But the final result here that I will show you, it's so it's here. The class, I think I have class center that I, no, this is not the class center I use for that. But anyway, I can still show you. So here, this is a result of, I use 5 class, and like you can see here, 5 class. But the main point that I would like to say here, it's the class blue, which is actually a high amplitude classes, which was seen, say, to be carbonate type of carbonate banks. For those who are familiar with the Scotian basin, so it was one class which was actually different with other. So this was as seen as a carbonate class of carbonate banks, which is in the formation of Abenaki in Jurassic carbonate formation. So like you can see here, depending on the type of data you have and depending on the target, the user can differently set the type of classes, the type of time gate. So I will quickly finish by showing you, for instance, the 3D UVQ that so actually the 3D UVQ, like I explained in the PowerPoint, I will not show some result here. Instead of using just one attribute, we will use different type of attribute. Like here, for instance, we use, if I can select just one, let me go to neural network, one which has been stored from file. Yeah, it has already even being selected already, sorry. So this is, for instance, five attribute which has been used as input. No. Yes, 5 attributes, spectral decomposition in different frequencies, most negative curvature, and horizon cube. And the result, like you can see, it's output seismic and match. I will just display in, I will not go through it, but I will just display, I'll cancel, I save it as attribute data, so I will just display it to show you how it looks like here. So match class neural network test. Yeah, neural network test number 3. Let me just go just to show you one of the results when using 3D type volume-based UVQ. So you cannot see it because this has, let me just display it in full. So this is just one of the results, but because the neural network is an iteration method, you can go back and change your attribute. So this hand, the webinar, Venice, back to you.
Okay, thank you, Eric. Now it is time for you to ask any question that you might have, or you write it in the question pane. We have open session now, so please go ahead. Anyone have any questions? Yes. Go ahead. I'm not sure if I will pronounce your name right. It's Oluwamulo. Go ahead, please. Hello? Yeah, you wrote your question? Okay. Okay, Frizo, I sent you a question.
Hello?
Frizo?
Hello?
Working on it.
Okay.
Yeah, let me read it first. I have some problems with my carry out. The question is if we can carry out the UVQ on both time and depth surfaces. Yeah, you can do that both very easily. The procedure works the same. And Eric already mentioned one very important thing to realize in this workflow is to geological reason a little bit about the time gate or the depth gate that you want to use. So it's important to think about how far the area of interest, the interval of interest extends either in time or depth, and also whether you have a conformable sequence or unconformable sequence. When you have an unconformable sequence, you often want to stay away a little bit from the area, the unconformable boundary, to avoid both side lobes from the unconformable terminations, as well as the differing acoustic contrast over unconformable interface, which is really not what you want to detect. So that are the main considerations, but for the rest, the workflow between the time and the depth is exactly the same. Does that answer your question? I guess you have to type your answer to that.
Okay, can you hear me, please, sir?
Okay. Is that answered your question?
Yeah, can you hear me? Thank you.
Okay, good. We have another question from Bill Overman, and I passed it to Farouk. So Farouk, if you can answer that question, please. Farouk, did you get my question?
Yes, can you hear me?
Yes, we can.
Okay. Yes, it's not a straightforward way, but you can apply it on a pre-stack gathering individually.
Can you repeat the question?
Ask the question.
Oh, sorry. Actually, the question is, can UVQ be applied to a pre-stack gather or not? So the answer is yes, but you will have to apply it on individual gather. It will be like an attribute type of unsupervised neural network, but not like a horizon-based UVQ or waveform segmentation.
Okay. We have another question from Nazir Ahmed. Go ahead, Nazir. You can say your question. Nazir? Nazir? Okay, I will pass his question. I don't know, he sent a question. What about data quality if we have noisy data?
I can answer that question.
Okay, because his mic is not working, yeah.
Yeah, data quality is of course an important item. If you go into the F3, if you do it on the raw data, you will see that your segmentation will also pick up an acquisition footprint. So you get striping in the inline direction, in this case through the area. So in that case, it is important to do some data preconditioning on the data, both to get rid of random noise as well as acquisition footprint. Then there's another pitfall that is, say, geological noise. I don't know if you can show the result on the upper horizon again real quick, Eric, the class.
Yep.
The other one, the really upper horizon in your tree.
Yep, yep.
And highlight the class values there.
Mm-hmm.
Hey, I might have a little bit delay in my screen here. I don't see it yet. Yeah, now you see it. If you go both to the upper north and to the south, you see those purple classes. Both are actually under shallow bright spots. And if you remember from the presentation from Eric, he showed that there was one class which was very low amplitude and low frequency. That was all the way, that was the class number 16. That purple class is that class number 16. So there you see basically a geological artifact that you have to account in your interpretation. You have to watch out for that, and that's kind of unavoidable. That you will have those things in your data. They're part of geology. And then third, sometimes you cannot do anything about the noise. You cannot condition them. Geological features are there, and then you just have to deal with them in the interpretation phase. Hope that answers your question.
Okay. Do we have any other questions? We still have a few more minutes if you would like to, if you have any more questions. On the same time, I just would like to know that.
Okay.
Yeah, David, you want to say something?
Well, one comment on that. I think Friso alluded to it. On conditioning the data, one thing we can do is a median dip filter on the data in order to get rid of some of the noise and some of the bad data. So I think that's one thing that's always a good idea very early in the process.
Okay, and also I would like to add, based on that question of the noise, we know that when you want to do your clustering, one of the first input is your horizon. So you should have a very good reference horizon. So if you have a bad data noisy, so that means that when you want to map, you cannot have a very good horizon which has been mapped in, let's say, one good event. So like David and Friso said earlier, just filter your data and you will reduce noise and enhance the seismic event and do your mapping once you have a very good reference horizon, you can start your clustering.
Yeah, actually, let me go back. That is a really good remark, Eric. You have to be really sure that your horizon is good, and that can mean two things. Generally, it means that your horizon is really well picked on one seismic phase, and you would see that quite quickly if it's not actually a UVQ classification. You actually see the wavelet window up there on the screen, and you see that the first sample is 4 milliseconds under the horizon, but you see that the horizon is probably picked on a seismic peak. Yeah. But sometimes horizons are composited because there are conformities or they go to different sedimentary environments, and in that case you really have to be sure that your horizon represents a geological timeline. They don't necessarily have to be on one phase, but if they are not on one seismic phase, you really have to be sure that they do represent one isochron.
Friese, did you see this comment that I sent you?
Yes, it's another question from, and I'm sorry if I mispronounced your name, Ulawal Pelumi. The question is, I understand you combine attributes together for the UVQ analysis. How does it differ from the spectral decomposition attribute analysis? What you will often see is there are two main differences. First of all, with segmentation analysis, it's a discrete result. You have different classes, and you're actually able to review the classes in the sense that you can look at the waveforms in this case. Like I have high amplitudes, low frequency, high amplitudes, high frequency. I have a little extra wiggle in it. So you have an extra tool to verify. Second, they're complementary. You can do also on this horizon MSS for a very successful spectral decomposition. And I would say 80% of the features you see are the same. However, there are crucial differences, like there's a difference in 20% that one method just picks up some geological features that the other method doesn't see, and they're kind of complementary in that sense. And then finally, the ability to review either your waveform to look for indications of DHI or a specific lithological response, or if you do it volumetric, to look at certain combinations of amplitude and frequency is really an advantage.
Yes,
okay.
I have one other comment, is that I think one of the very large advantages of the UVQ is especially in areas where you have low amplitude response in harder rock. And a lot of times spectral decomposition is sort of influenced by the amplitude of the spectrum. And a lot of times with low amplitude you can see changes with the UVQ that you don't see with spectral decomposition.
All right, thank you.
Okay, great. Any more questions? I don't see any other questions here, but okay, I think we had a useful webinar, and if you have any questions that you will think about after the presentation, please feel free to email us, and our email address is webinar@dgbes.com. And I want to thank you again for your participation with us. And if you happen to join us late, or you'd like to listen to this webinar again, it will be online in few days, and it will also be on our Facebook and LinkedIn page. I would like also to mention, since this is our last webinar in the year, if you have any suggestions for us, you have been listening to us month after month, if you have any suggestions for us or any feedback, we would like to improve, and we would like to help you more. So please feel free to email us any suggestion that you might have, that we can try to apply it if we can in the coming webinars. I'd like to say that DGB wishes every one of you Happy New Year, and we hope to see you again next year with us in our monthly webinar. Okay, bye-bye everyone.